We have solar cells represented, solar fuels, and bioenergy. We won't have a talk today on solar thermal. I'm going to say a few things more about solar cells, and I'll let the other speakers introduce solar fuels and bioenergy. There have been remarkable advances in photovoltaics over the last 5 or 6 years or so. And on this plot here, you can see in the solid blue, that's the price of the modules. And in the last 5 years, that's what's really come down remarkably from about $4 per watt to around 50 to 70 cents per watt, depending on who you ask. Then the upper, the green curve there, that's the total cost of installation. And what you see, one of the things that has shifted is that where more than half of the cost used to be in the module, now a very significant fraction of it is in the installation itself. And so there's still a need to work on that part of the problem. Solar is it's becoming economically competitive, especially here in California, and it's growing very rapidly, and we expect that to start to catch on in other states, and it's also doing very well in places like Saudi Arabia and China and Japan. On this plot, you can see the global installations, and it had been growing at about, typically it'll be about 30 to 40% per year growth. It leveled out a little bit last year, but it's still continuing to grow. And at about 35 gigawatts per year, and that's about the equivalent of installing 35 power plants. So solar is really starting to become a significant source of power generation. But we should not declare that the mission is accomplished. And solar panels are not completely ready. We should continue to do more research. The efficiency of most of the modules that's sold is about 15 to 20%. And if you can raise that, then you don't have to install as many panels. And so effectively, your installation costs start to go down. And so I think there's still important to push on that. And if we look at where solar is and where a lot of people think it can go, my best estimate is that we're about 2% there on the market size. And when you're only 2% of the way, you don't want to say, oh, we can stop R&D now. We have the panels that we need. And if you look at technology, most things continue to improve. And I think the solar panels in 10 and 20 years will be significantly better than the ones that we have now. And here are just some of the opportunities for improvement. In addition to raising efficiency, people would like to replace glass with plastic to lower costs, but also weight. There are a lot of roofs that can't handle the weight of being covered by solar cells. It's desirable to make the panels flexible and incorporate them directly into the roofing material, which is another way effectively to lower installation costs. But then, there are completely different directions. There's reducing the cost of permitting and finding customers. For me, a shocking statistic is that a lot of the companies pay 50 cents per watt just in advertising, marketing, and finding customers, because a lot of people call for a quote for 8 or 9 different companies and only pick one of the companies. So a lot of the money just goes right there. There's a need for figuring out better ways to finance solar cells, get the right financial packaging, and a lot of this also has to do with how the interest payments are taxed and how that stacks up compared to other kinds of energy investments. And then, perhaps beyond the solar itself, for solar to be widely implemented, we'll have to deal with the intermittency, and this is where a smarter grid can help, and if more people are driving electric vehicles, that may end up helping, especially if the utility can control when those cars are being charged. And then, of course, improving storage is a highly desirable thing, and batteries could come in there, but that's where the first talk will be on solar fuels, and if we harvest sunshine and generate a fuel instead of electricity, then we can address that. And finally, it never hurts to mention that a carbon tax would be helpful for the solar industry. And just to introduce a couple of the highlights, perovskite semiconductors have emerged in the last couple of years, and just a few years ago there was one research group looking at it and the efficiency was at 4%, and now I don't even have this up to date. The world record in just a couple of years has climbed up to 17.9%, and Professor Karunadasa will talk about how these solar cells can be developed in the second talk. Here within GCEP, one of the avenues we're pursuing to raise the efficiency is to make low-cost tandems, and the idea here is to leverage the silicon or the copper indium gallium selenide that is already commercially successful, and then put a high band gap solar cell on top of that, and that cell will harvest the higher energy photons and generate a higher voltage than the lower cell could. And one way to think of it is it's upgrading a product that already exists today. And so with that, I would like to introduce Will Chewy. He's a rising star here at Stanford in the material science department. He was the first professor hired by the Precourt Institute for Energy, and pretty much everything he does is energy related and almost always involving electrochemistry. And today he'll talk about solar fuels.
Okay, Mike, thank you very much for the kind introduction, and good afternoon. Welcome back to the afternoon session. So as Mike introduced, solar fuels is a very promising route for storing sunlight. And we're going to talk a little bit about the project we started 1.5 years ago on how to use both light and thermal energy to make efficient conversion of sunlight to fuel. I'd like to acknowledge the contributor to this work. This is a collaboration, close collaboration with Nick Maloche in the Material Science Engineering Department. The students, Xiaofei Ye and Madhur Belor, have been working on this, and postdoc Liming Zhang as well. So I always like to show this photo just because it's fun, and it also highlights the problem with sunlight. So solar energy is a funny business because it doesn't shine everywhere. It doesn't shine all the time. And if you look at the population distribution versus solar resource distribution, it's also greatly mismatched. So you have London, Tokyo, and Chicago. These are places with either variable, intermittent, or poor solar resource, and yet this is where the population lies. So this outlines some of the major motivations to develop technologies to be able to store sunlight so that it can be used when and wherever is needed. So one of the biggest challenge with solar and solar fuel is how do we increase the utilization of sunlight? And how do we do so with earth-abundant material? So let me briefly introduce what's being done now and how we are approaching the problem. So if you take a look at the solar spectrum, it's roughly 55% visible, 5% UV, and 50% infrared. And you can take a semiconductor material to absorb the sunlight, generate electron hole pairs, and that can then be reacted with water to make hydrogen and oxygen, and that can be later combusted to form water again and producing electricity, heat as needed. If you take a look at the plot on the lower right, that is the power of the sunlight as a function of wavelength. And you can see that we have a lot of sunlight at the large wavelength and the short wavelength as well. And if I have something like a 1.8 electron volt band gap semiconductor to absorb the sunlight, the part shaded in red is what I would take. Above and below the wavelength, most of the energy is either lost as transmission or lost as heat. So it would be great if we're able to harvest those heat in addition to the photon energy as well. So to date, most of these so-called photoelectrochemical cells or photocatalysts operate at room temperature. It is very effective at taking the sunlight, but it's not so effective at taking the thermal energy. And that's what we chose to focus on about 1.5 years ago at the beginning of our GCEP project. It is to look at how we may be able to take both forms of energy and use that to increase the efficiency, the stability of the materials, and also to decrease the use of precious materials like platinum. So the very first thing we did is to take a look at the economics, the efficiency. So is this a promising technology, theoretically speaking? So what we did is we simulated what we think to be a good solid-state photoelectrochemical cell that can operate under a wide temperature range, all the way from room temperature to 1,000 degrees Celsius. The materials for this does not exist today, but we made a simulation nevertheless. And what we found was really quite surprising. If you look at the plot on the left, that shows the amount of energy that comes from the light and that comes from heat as a function of temperature of the solar field generator. So as you go from room temperature, so use mostly what we call the electrical energy, so that's the energy that comes from the generation of electron hole pairs. But as you go up in temperature, say for example at 400 or 500 degrees Celsius, then you get a significant thermal contribution to the efficiency. So you can see the y-axis is essentially the efficiency you can hit. As you go from room temperature to 400 degrees C to 500 degrees C, you have a significant rise of the efficiency, and most of it actually comes from an increase in the thermal contribution to the amount of energy stored in the fuel. We also looked at as a function of material properties. So the plot on the right is a parametric plot of the operating temperature in Kelvin and the band gap of the material. And the color shows you the predicted efficiency of the system, accounting for various loss terms. And this contour plot shows that at intermediate band gap, approximately 1.8 to 2.4 electron volts, and at elevated temperature, 800 Kelvin, you can actually hit the sweet spot of the solar to fuel efficiency. And we estimated upwards of 20% as possible, which is a significant step beyond what we can do today. So with the theory understood, then we begin to explore actual material that can enable us to get to these temperatures of interest so that we can harvest both the thermal energy and the photon energy as well. One of the interesting things I would like to talk about today is how can thermal energy make existing materials better? So I show a picture here. It's rocks that's composed of mostly iron oxide. This is a material that is of great interest to the solar field community because it's abundant and it is extremely stable. It is the most oxidized form of iron. So this is a material that exists in nature. Sometimes it's called hematite. It's Fe2O3. The problem with materials like iron oxide, and another one I will talk about next, is there is not a very good semiconductor. So if you consider any photovoltaic-based process, you have to be able to absorb sunlight, then you have to be able to generate electron hole pairs, and you have to be able to separate them, just like any other solar cell. The problem with a material like iron oxide is that the electrons and hole move very slowly in the material. So the possibility for them to come back and generate heat is fairly large. The reason why iron oxide is not a very good semiconductor is because the mobility of what we call the minority carrier, the electron in this case, is very, very low. So the electron barely moves, and this is due to a strong interactions of the electrons and the ion in the crystal lattice. So here I show you a plot of the mobility of silicon and the iron oxide as a function of temperature. And you can see silicon's way up there. It's about 10 to the 2 centimeters squared per volt per second. And iron oxide actually has mobility that is immeasurable at room temperature because it's so lousy. But what you can see, a very significant contrast between the two materials is the slope on temperature. So while silicon decreases slightly in mobility when you increase the temperature, iron oxide actually increases dramatically, exponentially with temperature. So here we propose that increasing the temperature, which comes from the incorporation of thermal energy into photoelectrochemical cells, you're able to increase the minority carrier mobility so that you can separate the charge better in the photoelectrochemical cell. I should know there are very little routes you can envision which you can improve the mobility of a minority carrier in a semiconductor. You can think about doping, but that just increases the concentration of the majority carrier. There is not another route. If you nanostructure, that's fine too, but again, you're not changing the mobility. So the fundamental limitation of these highly stable, abundant material like iron oxide is simply that the mobility isn't good enough at room temperature. So let's up the temperature and see what happens. So we first examined this iron oxide as a thin film geometry. In my group, we do a lot of fundamental research with model systems. So we use pulse laser deposition to make a very thin 30 nanometer film of iron oxide on a platinized sapphire substrate. And you can see we were able to make very, very high quality structure. This is a little bit in contrast with the nanostructure that you see with PECs, but this allows us to control the morphology perfectly. And what we did next is we designed an apparatus not only to control the light incident on the cell, but also to control the temperature among various other things. So the setup on the left shows that we have a thermostatic controller, a water bath basically, to set the temperature of the cell. And we have a liquid electrolyte system that allows us to go close to 100 degrees Celsius. So this is a liquid-based system, so we're capped basically by the boiling point of water. So this is a standard electrochemical experiment, but we have very precise control of the temperature of the cell. In addition, in order to achieve higher temperature, typically optical concentration is needed. You have to focus the sunlight a little bit. So we also have a concentrated solar simulator so we can focus the sunlight down to upwards of 9 times the solar radiation without concentration. So on the right, I have a couple of plots that shows the performance of this material. On the top is what we call the IV curve, the current voltage curve under illumination. At the bottom, it's in the dark. So if you haven't seen this before, essentially we want to push the curve to the left as much as possible so it has sufficient potential to dissociate water into hydrogen and oxygen. So what I'm showing you is several curves of these iron oxide semiconductor at various temperatures starting from 7 degrees Celsius to 72 degrees Celsius at 2 different optical concentrations. So again, we have 1 sun, so that's what we have out there. Not today, but if the sun was out, it will be 1 sun. And then 9 times that, okay? So I want to point out several critical features of the plot. So if you look at the plot on the top, as you increase the intensity of the sunlight, the current goes up proportionally. So this is a great news. So this means we're able to shrink down the size of the cell and still achieve the same current. This doesn't happen everywhere. Depending on how good the materials at separating charge, you might not get a 1-to-1 improvement. So here, when we increase the optical concentration, we have a corresponding increase by 9 times in the current, thereby achieving something that's quite nice. Then when we increase the temperature, you can see the voltage actually moves slightly to the right. So as I mentioned before, we want the voltage to go to the left, so this is not the best situation. Now if you turn your attention to the dark current voltage curve, you see actually the curve is indeed shifting to the left if you don't have any light. And what's more important is that when you increase the temperature, the driving force needed to break the water molecule decreases as well. And I note that with the 2 voltages on the bottom, it decreases by about 50 millivolt, But the actual voltage decrease we see, the shifting to the left of the plot, is actually much more significant. So from the bottom plot, we can conclude that by increasing the temperature, we're putting thermal energy into the electrons and the molecules to improve the rate of electrocatalysis. So even without light, iron oxide is functioning as a better material. And when we put the light in, it decreases a little bit. The shift is smaller than the gain you're getting, so that's good. And then furthermore, if we concentrate the light, we're able to substantially increase the current. And also by increasing the intensity of the light, you're also shifting the voltage to the left as well. So by carefully playing with temperature and light intensity, we're able to do what we want, which is push the voltage to a lower value on this plot and push the current higher. This is just a plot showing you the enhancement. We were able to take the curves from the previous slide and decouple it into various contributions. Here I'm showing you the relative potential, so this is the relative voltage, if you will, compared to the baseline case, which is room temperature and 1 sun, no optical concentration. As you can see on the top case, when we increase the temperature without increasing the intensity, you have a general movement to the right. So you have the so-called onset potential. This is when the current starts to take off. It's moving to higher values, so this is not good. The photovoltage is also moving to smaller values. That's not good either. But the overpotential is decreasing, so this is the amount of excess driving force needed to catalyze the reaction. And also, the equilibrium voltage, so the thermodynamic voltage needed to break the water molecule, is also decreasing. But on a net basis, you're losing. But on the second row, where we have increased temperature and increased optical concentration, then we have everything moving in the right direction. Sorry, that means everything moving in the right direction to the left. So you have the thermodynamic driving force needed decreasing. You have the overpotential required decreasing. You have the photovoltage actually increasing slightly. And then you have the overall onset potential, so this is where the current starts to take off, also decreasing by about 70 millivolt. So this is a considerable first step to demonstrate that it is a good idea to put in light and heat into the photoelectrochemical cell to improve the efficiency. The increase is relatively small here because we're going to very moderate temperature. We're only increasing the temperature here by 60 degrees Celsius. And I will discuss a little bit on the opportunities to go much higher in temperature. But this is not the best part of the story. For those familiar with solar cells, one of the key characteristics of solar cell is the so-called fill factor. The fill factor basically tells you how fast your voltage increases with potential. Ideally, we want something kind of like a square rather than a slanted line on this curve. And what I'd like to point out to you is the current actually rises much faster with potential when you increase the temperature. And I can show you this better by blocking out some of the data. So if you just focus on the range between 0.3 and 3 milliamp per square centimeter, you can actually see the curvature changing. So when the temperature is low at 7 degrees Celsius, it's quite a bit curved. And when you increase the temperature to 72 degrees Celsius, the curvature decreases substantially. So this means that the amount of excess voltage you need to get to the high current you want is now less. So let me plot that. I'm basically showing you here the voltage difference needed to go between these two currents. So the voltage difference needed to go from 0.4 to 4 milliamps. Okay, so this is the extra voltage needed. At 7 degrees, you need to give about 300 millivolt in order to achieve a 10-fold increase in the current. But in the case of 72 degrees C, you only need about 200 millivolt. And the difference is about 160 millivolt. So in the previous slide, I showed you how the onset potential, so when the current starts to take off. This plot is showing you how high current behaves. And this is actually where it matters because we will not want to operate our cell at very low current. So this tells you by increasing the fill factor with thermal activation, you're able to achieve higher current with less applied potential. And the reason for this, we have shown is due to the increased, much improved mobility of the minority carrier in iron oxide. So we're better able to separate the charge, and that's leading to a much faster rise of the current with voltage. So that's the first material we looked at. The second material we looked at, which also turns out to be one of these low mobility semiconductor, is bismuth vanadate. This is being a material that's heavily investigated in GCEP programs and elsewhere, and it's a very promising material because it exhibits a very significant photovoltage. But one of the not so well-known fact about this material is that the electromobility also sucks. And by increasing the thermal energy into the system, we have the opportunity to also improve its photochemical properties for converting sunlight into fuel. So I just show you here some scanning electron micrographs. These are the nanostructure we have created through a series of electrodeposition and pyrolysis reactions. We tried doping the system to improve the conductivity of the majority carrier. We also added catalyst to it. But without showing you too many details, essentially we're able to create state-of-the-art bismuth vanadate material for photoelectrochemical cell at room temperature. So the next thing we wanted to do was to see how thermal energy could improve the performance of the material. Well, we saw actually an even more dramatic dependence on temperature than iron oxide. In the case of bismuth vanadate, when we increase the temperature, the current under illumination versus voltage rises significantly with temperature. If you take a look at the higher voltage part, you can see that the current actually increases by almost 50% as we go from 9 degrees Celsius to just 42 degrees Celsius, just a very small temperature increase. And then simultaneously, the voltage barely changes, the onset voltage on the bottom. So this is great because we're maintaining a very high power output of the photoelectrochemical cell. We further investigated this. We wanted to know exactly how much the open circuit potential is changing, and we did a rigorous measurement of the open circuit potential of the cell, and we saw that the voltage declined at about 3 millivolt per Kelvin. And you can see the plot on the lower right, at various concentration, that's at 1 sun and 3 sun concentration, we have an open circuit potential close to 800 millivolts. And we're losing some voltage, absolutely, but we're gaining a lot more in the current. So you can see with the temperature, we're gaining substantially higher saturation current. And the reason is, again, you're getting better electron-hole charge separation, so these carriers has a better chance of reaching the water molecule to split it into hydrogen and oxygen. So people always ask me, well, increasing the temperature generally decreases the stability. Well, it turns out that's not so much the case here. For both the iron oxide and the bismuth vanadate, the stability is actually rather good. So on the left plot, we have the iron oxide. This is where we held the current constant and we monitored the voltage. For the bismuth vanadate, we did the opposite. We held the voltage constant and monitored the current, and just because 2 different people did the experiments. And we can see that the stability is excellent. The ripples you're seeing is due to the formation of bubbles on the top of the photoelectrode, so don't worry too much about that. But the bottom line is that we have stability over a relatively short period of time, 5 hours. But we have seen stability upwards of 50 hours is also possible as well. And we're working toward improving the stability of the system at even higher temperature. So if I were to summarize the results so far, the concept of a thermally enhanced photoelectrochemical cell is appealing to us because of the following. In the left, you have the standard case of non-concentrated light hitting on a photoelectrochemical cell or solar cell. So this is the baseline case. One possibility in the second case is you can concentrate the light, but in the case of solar cell, you usually have to cool the solar cell because the power output of the solar cell decreases. So you have to have active cooling. This has been a challenge with the field of concentrated photovoltaics because the expenses associated with cooling and system complexity. What we show here is the third case. With photoelectrochemical cell, it is not necessary to cool it. In fact, we wanted to heat up because the extra thermal energy can improve the total current and the voltage output of the cell, and therefore improve the efficiency of sunlight to fuel processes. So this is my last slide. All is great. We can go up to about 100 degrees C, but then water boils, then we're out of luck. So actually, the main thrust of our GCEP work is to look at how to take the liquid cell up into a solid state cell in which the temperature can go far beyond 100 degrees Celsius. So we essentially take the liquid electrolyte and replace it with a solid electrolyte. That can go much higher in temperature. These are typically ceramic materials. And then to achieve the type of temperature needed, say 400 or 500 degrees Celsius, this is where I showed the efficiency simulation to exhibit the highest value. We will need also some sort of solar concentration system as well, and I showed just one possibility of using a heliostat field, and we're working very closely with industry to think about a system-level implementation. So with that, I would like to conclude. I've showed you some preliminary results of liquid cells with significant improved efficiency just by modulating the temperature. And I also show you the possibility here to go much higher in temperature. So next year, I hope to share results on the solid state cells, which we can hopefully achieve efficiency that matches our predictions. And with that, I'd like to acknowledge the support from GCEP, its sponsors, and also the Precourt Institute for Energy. And thank you for your attention.
Okay, are there any questions?
Very nice, very interesting. It's interesting to me, though, that you're going to be, one of the things you want to do is split water and then burn hydrogen later on at perhaps 50% efficiency. And the sun conversion that you're doing is, what would you suggest, 10%, 20% efficiency?
That's an excellent question. So the sunlight to fuel, I think if we can hit something like 20% or even a little bit higher, that's already a very, very good performance. And then if you want to combust the hydrogen, I certainly would not be advocating to burn it. If we run it through a fuel cell, then we can get efficiency upwards of 90%. But once you have hydrogen, it serves as an excellent precursor molecule to do other things as well. For example, we can perform hydrogenation of carbon dioxide. So that could be one route toward making liquid fuel. So hydrogen is just a starting point. I should also emphasize the type of chemistry we're exploring is not limited to only water and hydrogen. We're also pursuing very strongly CO2 chemistry, so we can reduce CO2 to carbon monoxide. Again, that is a precursor. So if we have hydrogen and CO, that's synthesis gas, and we can pretty much do everything from there as well, from the chemical engineering perspective. So I hope that answers your question.
Yeah, there's one other thing having to do with the heliostat system. If you do that, the purpose there is to generate electricity or to generate hydrogen?
Yes, the purpose there is just to provide a mechanism to provide for the optical concentration. So as you saw here, it is not possible to reach the type of temperature we're talking about without moderate optical concentration. And here we are envisioning that we can pick it back onto development of existing solar concentration technology, and the cost is decreasing every day in the solar thermal electricity generation. So the vision I would have is that part of the solar thermal plant will be generating electricity during the daytime. The other part of it will be generating fuel. And at nighttime, this then can be used for dispatchable electricity without the sun. Or you can think about multi-day dispatchability. If it's bad weather in the winter, then you can have fuel for a couple days to run. So therefore, having a very equalized output of electricity from the solar thermal system.
A very good talk. Now, your quantum yield at this point is very low.
Very low.
What do you think is limiting your quantum yield, and what do you need to do to get to a point to be practical for hydrogen generation, for example, in the 5% quantum efficiency?
Yeah. Well, actually, in our bismuth vanadate work, the quantum yield is already very good. We're comparable to the best reports in literature. Actually, in this case, the main problem is the voltage. Because the voltage naturally declines with temperature, so we always have to make sure we have enough voltage input, and we don't want to have to put in extra voltage into the system. So what we're looking at now is to increase the voltage output by, for example, selectively removing the electron holes with selective contacts. We're also looking at heterojunctions so we can better separate the electron hole pairs so that we can retain the high voltage that you would have room temperature but at elevated temperature. So I think the voltage is the primary challenge going forward.
Hi, Will. Excellent
Andrew,
presentation.
hi, thank you.
I was wondering if you could comment on the use of catalysts or not at higher temperature, and you're thinking on why you would or wouldn't want to use them, and maybe the effect on stability as well.
Yeah, that's a great question. So if we take a look at other high temperature electrochemistry fields, such as high temperature fuel cells, actually platinum and other precious group materials are not the best performance. It turns out metal oxide, inexpensive metal oxide catalysts are the best at high temperature, not the precious materials. So I foresee that the catalyst use will be non-precious, it will be quite low, and because they're metal oxides, mostly refractory, high melting point metal oxides, the micro nanostructure will be extremely stable at high temperature. So there we can draw from the deep expertise within the high temperature electrochemistry community to try to build up a earth-abundant catalyst system for our photoelectrochemical cells.
Okay, let's thank Will for an excellent lecture.
Thank you.
Okay, our next speaker is Hema Karunadasa, and I believe she's in her second year as an assistant professor in the chemistry department here at Stanford, and her entire research group develops perovskite materials for various applications, and today she'll talk about her GCEP project on using them for solar cells.
Great. Thank you, Mike, for the introduction, and thanks also to Sally and Richard for the invitation to speak. I'm really thrilled to be here today to tell you a little bit about our very recent results in hybrid perovskite solar cells. So this is a collaboration between my group in chemistry and Mike McGee's group in material science and engineering. And we are a bunch of synthetic inorganic chemists, and together with Mike's group in engineering, we both synthesize new materials that could function as solar cell absorbers, and we also test these materials in actual devices. So to start, I want to So to start, I'd like to start with the structure of this material and try to explain to you why there's so much excitement about hybrid perovskites in the photovoltaics community. So perovskites are a huge family of compounds, and these materials have been known for many, many years. In fact, the first work on perovskites dates back to the 1800s. And you can form perovskites with metal oxides, metal sulfides, metal halides. And these materials have very versatile electronic structures as well. So you can form perovskites that are high band gap insulators, semiconductors, conductors, even high temperature superconductors. These materials are everywhere, and these properties of perovskites have been exploited for many decades. And these materials have this, the same general overall structure. Here I show you the structure of this lead halide perovskite material that has caused so much excitement in the photovoltaics community, where the inorganic framework just consists of a very simple framework of lead halide octahedra that share corners. And this extends out in all 3 dimensions, and this framework has a net negative charge. So therefore, to provide charge balance, we need very small positive ions that have to reside within the cavities of this structure. So within each cavity that's defined by 8 corner-sharing octahedra sits a very small organic cation. Well, it can be either an organic or an inorganic cation. In the case where we put a very small organic cation, like this methylammonium that I've just shown as a gray sphere, these materials are called hybrid perovskites. But there are many related materials which can be structurally derived from this overall structure. So today I will talk to you about both this 3D structure shown here, as well as a family member, which is the 2D material. And you can again think of the 2D material as if you took your 3D perovskite and took a very fine knife and started slicing layers of your 3D structure. And again, you get this an extended two-dimensional array of corner-sharing lead-iodide octahedra. But now you have this additional advantage for, at least for structural tunability, which is that between these sheets, you can put much larger and potentially more elaborate organic cations. And later in the talk, I'll tell you why you might want to work with both the 3D as well as the 2D structures. So one thing that continues to amaze me about these materials is that they form on their own accord. This is called solution state self-assembly, which means you can just take a beaker, put it on your bench, and just throw into solution your precursor ions. So you can throw in the halides and the metals and the organic cations. And if you just tune your conditions just right, these materials form on their own. And the beauty of self-assembly is that whenever you get molecules or ions to do what they want to do, they do it perfectly well. So when you get the conditions just right, you can isolate these hybrid perovskites as crystalline powders, thin films. And in my group, we love to grow single crystals because they are beautiful, and also because you can do very precise measurements on well-formed single-phase single crystals. In fact, every picture I show you is from a single crystal X-ray diffraction study. So I want to discuss some of the strengths of this material. There are many. I'll just highlight some of the points that I think are worth mentioning. A very important point about perovskite adsorbers is that these materials can be formed through solution state methods, which makes everything extremely inexpensive. The precursors are very cheap, and you can use solution state methods like spin coating, drop casting, or vapor conversion methods to make these materials. So here I show you a schematic of one particular way to make nice films of hybrid perovskites, where we can simply take a mesoporous titania scaffold and drop a solution of lead iodide into this material. The solution will coat the scaffold and form this nice layer of lead iodide. Lead iodide forms a layered structure, which means that it likes to form uniform films around any kind of scaffold. And lead iodide is yellow, so we get this yellow film. We can then simply take this film and immerse it into a solution containing methylammonium iodide, and the methylammonium iodide will work its way in through the lead iodide film and convert that film into the perovskite. So our yellow film is turned black, and we are left with this beautiful uniform film of the perovskite. We simply heat this film, drive out any volatiles, and we're left with a nice film that we can then continue to fabricate the solar cell device. So that makes everything very cheap and very scalable. I think this is the chart that I stole from Mike's slides that gets everyone really excited about these materials. There's been a very, very sharp increase in the efficiencies of these materials over a remarkably short period of time. So the first solar cell, as Mike mentioned, the paper came out in 2009, and this was a really neat result, but it kind of stood alone, and it was more of a scientific curiosity. And then in just a very short time, these efficiencies got to the point where everybody cared very deeply about these materials. And there's certainly no sign of plateauing, so we can most likely expect further increases in the efficiencies of these materials. 2009 was a very memorable year for me. I was writing my PhD thesis when the first paper came out, and I just read this paper and thought, oh, that's neat. But then by the time I started my group in 2012, things got a lot more exciting. And this was a great, great subject to work on. So I'll tell you some of the reasons why these materials have these great efficiencies. It's very remarkable that these materials have very intrinsic properties in its photoexcited state. So when we hit these materials with light and we create photogenerated electrons and holes, these charge carriers can move around very freely. The diffusion lengths are very long, and they don't recombine very easily, which means we get ourselves some time for those holes and electrons to go their own separate ways and complete the external circuit in the solar cell device. And these materials seem remarkably tolerant of defects. In fact, you don't need beautiful single crystals of these materials to realize very high charge carrier mobilities. Even polycrystalline powders behave very well, and even films, which is very strange and very unusual for solar cell adsorbers. And this is the typical diagram we show when we talk about the energy levels of a solar cell adsorber in contact with charge carriers. So the basic idea behind a solar cell is that we have a semiconductor, This is your adsorber, so in this case, this would be the perovskite. And we hit this material with light corresponding to this band gap energy. And the idea is that we excite an electron from the filled valence band shown here to the empty conduction band shown here. We now need to separate those electrons and holes and send them their separate ways. To do that, we need materials that can conduct the electrons and conduct the holes. So the way that we can move this electron to electron transport material is to drop it in energy. And the way we can move these holes is to raise it in energy. Holes, that's just an absence of an electron. So raising the energy of the hole stabilizes it. So by necessity, this diagram shows nicely that the voltage you can get from a solar cell is smaller than the band gap of the adsorber, because just to be able to transport those carriers, we had to drop the energy of the electrons or increase the energy of the holes. But some very interesting recent reports have shown that these perovskites are not just great adsorbers, but they can also transport charge very well. So imagine getting rid of this electron conductor. In this case, your adsorber is both the adsorber and the electron conductor, which means you just bought yourself a lot more voltage, a lot more obtainable voltage. So this has been shown for both electrons and for holes. So perovskites are really versatile materials. And a very nice attribute of these materials is, again, just through solution state self-assembly, we can start adding different ions into the lattice. So we can start with a lead-iodide lattice and then start doping it with bromide, and we can change the absorption energy of the material. And you can see that there's this nice increase in band gap as we start adding bromide into the lead-iodide lattice. And being able to tune the band gap of the material is very interesting for lots of applications. With respect to solar cells, Mike mentioned that his group works on tandem devices, and they have indeed shown that tandems can work very well. In a two-adsorber tandem device, the higher adsorber, the band gap of the higher energy adsorber has to be about 1.9 EV. So with lead iodide alone, we get a band gap of about 1.5 EV. So in order to get to 1.9 EV, one potential strategy is to incorporate bromide into this structure. I'll get back to whether we can do this or not, but the fact that we can tune the band gap is very exciting for applications as solar cell adsorbers, light-emitting diodes, and lasers. It's very cool to think that we can simply change the structure and change the color of the light that comes out of this material in a laser. So these are, I hope I've convinced you that these perovskites have very promising properties, and I love perovskites. I'm a huge advocate of these materials, and I very much want to see this technology work. But precisely for these reasons, we've decided to focus on the weaknesses of this material, because we want to identify any problems that we might find in these materials so that we have a chance of addressing them and hopefully resolving them. So for the rest of my talk, I will focus on the weaknesses, the potential problems that we might encounter using these materials. There's no denying the fact that there's lead in this material, and a lot of it. There's a lot of concern that this lead is not just toxic, but these materials are water soluble. And there are many people who say we've just removed the lead from our houses. Are we really going to coat our roofs with lead back again? So this might boil down to just an encapsulation problem. But for now, there is some concern about the toxicity of the lead, particularly a water-soluble source of lead. Another problem that we have seen in our labs, we've seen this firsthand, is that these materials are not stable to moisture. So we can form nice uniform black films of this material, and here's a nice annealed film of the 3D perovskite, and if you just let it sit on the lab, on a bench in the lab, over the course of a few days, I hope you can see this, there are these yellow patches that start forming on the surface of your film. So it's bad news when your black solar cell adsorber turns yellow. That means it's not absorbing sunlight. So these yellow patches are lead iodide patches that form. This material converts to lead iodide in ambient moisture. In fact, you can see this even more clearly in the absorption spectrum. This is the band gap of your perovskite, and over time, you see that this band gap decreases, and there's this higher energy band gap material that forms. This shows that the perovskite material is decomposing, and lead iodide is forming instead. And the final point I want to bring up is something that has become more apparent recently. I told you that by adding bromide into this lead iodide lattice, we can change the band gap. So we can form materials that have a band gap of 1.6 using a lead iodide lattice, as well as a material with a band gap of 2.3 EV using a lead bromide lattice. And by using intermediate stoichiometries of lead and bromide, we can actually access all intermediate band gaps. But when we look at the voltages that have been achieved using these materials, the lowest band gap material gives a low voltage, the highest band gap material gives a high voltage, but the intermediate band gap materials do not give higher voltages than the lead-iodide material, and this is very curious. So we decided to investigate why this might be as well. So we have efforts in both our groups to address all 3 points, but for the rest of the talk, I will focus on the last 2 points and show you our efforts on trying to make a more moisture-resistant material, a lead perovskite with greater resistance to moisture. And I'll also talk to you about our investigations on why these mixed halide materials don't deliver the high voltages that we expected them to give us. So I show you again the picture of the 3-dimensional perovskite. It's a beautiful structure, but for a synthetic chemist trying to make a material modification, this can also be a very frustrating structure because there isn't much we can do. So if we want to maintain the beautiful adsorption properties of this inorganic framework, we really don't want to mess with the inorganic structure. So that leaves us with only these very small organic groups to play with. This cavity really restricts the size of the molecules that can enter this structure. So if we want to improve the moisture stability, we could swap out this cation for another small cation, but there isn't much we can do. We wanted more space. So we took a step back and looked at some related materials that we had been studying before we moved on to 3D perovskites. So in my lab, prior to our work on solar cells, we had been working on the layered perovskites that I showed you in one of my first few slides. So these materials have just one inorganic sheet sandwiched by organic layers above and below, and this is a repeating unit. And I'm going to call this n equals 1. This has a very large band gap, and this has very high exciton binding energies, which means when you hit this with light and you generate electrons and holes, these charge carriers are very strongly attracted to each other. In fact, these have all the properties that you seek to avoid in a solar cell absorber. And we know that these materials have other advantages. We've found that some materials which have these n equals 1 sheets are actually very nice phosphors. So when we hit this material with blue light or with UV light, the material emits white light, broadband white light, which looks like sunlight. And we know that the reason you get this emission is because this layered material gives rise to electronic structures, which induce very strong exciton binding energies, as well as very localized charge carriers. And we know that if you were to simply expand the thickness of this inorganic sheet all the way to n equals infinity, we know that we can decrease the band gap, and we know that we can also decrease the exciton binding energy. And we also know that these two are extremes in what's really the continuum of the hybrid perovskite family, so we decided to make the intermediate species. And you can see that there's this nice change in the electronic structure as we go from n equals 1, 2, 3, all the way to infinity. The band gap decreases, and most importantly, the exciton binding energy decreases. So now when we generate these charge carriers, they don't recombine. They can move around, and they're free from each other. So Ian Smith, in my group, crystallized the first n equals 3 lead-iodide perovskite. He formed single crystals of these materials. This is the crystal structure. And he decided to make a solar cell with this to investigate whether n equals 3 was thick enough to generate photocurrent in a solar cell device. I will give a brief description of Ian's work here, but Ian is giving his own talk today later on in the symposium. So he constructed a planar geometry solar cell device where he basically used titania, a flat layer of titania as the electron transport material, deposited the layered perovskite as the light absorber, and spun an organic hole transport material on top of that, and he found that this material does indeed work as a solar cell. Our first generation devices have power conversion efficiencies of about 4.7%. And this compared to the highest efficiencies with 3D perovskites, which have now reached about 18%, is a low number. But this is not an optimized device in any way. And I'd like to discuss some advantages of the 2D material with respect to the 3D structure. So for one, this has a larger band gap, so we can access higher voltages. These voltages are higher than any voltages that have been achieved with the 3D perovskite solar cell. These materials are layered. The structure is layered, and therefore they grow as plates. This is in contrast to 3D perovskites, which grow as cubes or blocks. And because of this layered structure, these materials love to form beautiful uniform films. So we can simply drop cast this material on a slide and this doesn't require any kind of high temperature annealing. We can form nice continuous films. And here I show you a film of the 2D perovskite, and in contrast, similar deposition techniques for the 3D material don't give the same nice surface coverage. And by far, I think the most important point here is that the 2D material is a lot more stable to moisture. So with the 3D material, here I show you powder XRD patterns, and over time, we see when this is exposed to about 50% humidity, we see the growth of new peaks, which completely dominate the spectrum after about 40 days. This is lead iodide, whereas in the 2D material, this material is pristine, untouched by lead iodide over 40 days. So we think that there might be a critical value of N where we can make the inorganic layer just thick enough that it pretends it's a 3D material and has all the beautiful absorption properties of the 3D structure, while the organic functionalities can bring new functions into these materials. So you can imagine putting fluorocarbons here. This would look like you've taken your 3D material, sliced it, and coated those sheets with Teflon to improve the moisture stability at the atomic level. And we can imagine even molecules that absorb light or transport charge to bring new functionality to these materials. So with the rest of my time, I'm going to switch gears and talk to you about some very curious properties we've seen in mixed halide perovskites, in 3D perovskites. So here I show you again the band gap of these materials as you dope in bromide to the lead iodide lattice, and you see this nice increase in band gap energy as a function of bromide content into this lattice. And if you look at the photoluminescence spectrum of these materials, again, as we expect, we see that the energy of the emission goes to higher energies as we have more bromide in the material. This is exactly as we would expect, and we get this beautiful series. But Eric found that if he kept shining the light on these materials just at one sun illumination for just about a minute, this material changes dramatically. So he finds that as he keeps illuminating these materials, the initial photoluminescence starts to die down. And a new photoluminescence band starts to grow in that gets very high in intensity at around 1.7 EV. Curiously, it doesn't matter where the initial photoluminescence band begins, they all merge, and the eventual photoluminescence arises from this band at 1.7 EV. So the all-bromide material does not show a shift in PL, the all-iodide material does not shift, but every other intermediate stoichiometry changes and moves to this material that emits at 1.7 EV. And what's really surprising to me about this transformation is that it's reversible. When you turn off the light, you regenerate the initial material, and when you turn on the light, you get this new low-energy PL, and you can cycle between this. Eric has done this several times. Here I show you data for 4 of these cycles. So we decided to study this material under illumination to figure out what on earth was going on. And we did several experiments. So here, Eric sees that under illumination, a new sub-band gap shoulder grows in at around 1.7 EV. And again, when the light is turned off, the shoulder decreases. Light is turned on, the shoulder grows in, and so on. This can be cycled. And Eric then wanted to study the structure of this material under illumination. So he decided to look at the X-ray powder diffraction pattern of these materials under illumination. So he employed this very sophisticated experimental setup where he suspended a bicycle lamp inside the diffractometer. And he just turned on this lamp, and this was enough to cause a change in the powder pattern of this material. When the light is turned on, he sees that every peak is split into 2 peaks. And when the light is turned off, he sees that the original peak grow back in. And these split peaks show the presence of a material with a larger lattice than the original, as well as a material with a smaller lattice than the original mixed halide perovskite. So we went to the electronic structure of this material to try and understand what might be going on here. And here I show you for the x equals 0.6 material, the valence band as well as the conduction band. When we hit this with light, there are holes in the valence band and electrons in your conduction band. We know that initially, the photoluminescence comes from these electrons falling from here to here, But in time, we get this low energy photoluminescence band, which means we're forming a trap. So here's my trap. We have some state where the holes fall into a state with lower energy. We know that the energy of this photoluminescence corresponds to the same energy as the photoluminescence from an x equals 0.2 material. So we ask the question, maybe why not form the x equals 0.2 material, but only under illumination? So our speculative mechanism can be summarized with this picture. We have this homogeneously mixed bromide iodide lattice, lead bromide iodide lattice, but when we shine light on this material, there's halide segregation that is initiated by the illumination. And here, my darker blue squares show areas of higher iodide content, and these lighter blue squares show areas of lower iodide content. So there's halide segregation under illumination, and all the holes, of course, will move to the lower energy material, which is the iodide-rich material. And therefore, we get photoluminescence only from that trap. And our data so far support this speculation. If we were to fit this shoulder that we see emerge in the light-soaked material, that actually corresponds quite well to what we would expect from the absorption spectrum of the x equals 0.2 material if about 1% of that material converted. And if we were to form regions of high iodide content, that means we must, by necessity, form regions of low iodide content as well. And that also explains the split diffraction peaks, because here, this peak matches well with the x equals 0.2 material, and this peak matches quite well with the x equals 0.8 material. So halide segregation implies halide motion under illumination. And we know that this is a thermally activated process, because at different temperatures, we see different rates of this photoluminescence band growing in. And we can calculate an activation energy for this process. We get a number of about 2.3 eV. And this number fits very well with activation energies that have been attributed to halide migration in other metal halide perovskites. So just to end, I want to summarize this section. We see very interesting reversible changes in these materials upon illumination. So far, our observations are all consistent with halide migration initiated by stabilization of these holes through halide segregation. And we see this behavior even if we were to change the organic ions in this material. We see this behavior in films formed through all the deposition techniques mentioned in the literature for making these materials. We see this even in single crystals of the material. So we know it's inherent to the material and not due to any weird surface sites. And though I think this is incredibly cool, in terms of solar cells, this restricts the voltages that you can obtain from mixed halide perovskites. And if you really do want to form higher voltage perovskites, we need to either try to prevent halide segregation in these materials or look at alternative strategies to increasing the band gap. So for example, changing the metals or working with the lower dimensional 2D materials that I talked about previously. And I'm out of time, so I'll end there. I want to thank my group for the inordinate amount of hard work they put into their work. The students in my group and in Mike's group who have directly contributed to the GCEP efforts are listed here, but we often rely on the combined expertise of all members in both groups to move our work forward. And I'm very grateful for GCEP's support of this work that has really accelerated our collaboration. I'm done. Thanks for listening. I'm happy to answer questions.
Okay, do we have any questions for Hema? Bruce.
The result of the light-induced segregation is the first instance I've seen of a light-dependent solubility. So it seems as though the solubility is one number without light and another number with light. And so have you ever seen this before? And it can't be a kinetic effect because it goes back and forth. So
Yes.
You're changing somehow the thermodynamics of solution with the light.
Yes, I have seen cases of this previously where the migration was not reversible. So light-induced halide segregation has been noted in lead halides, in silver halides. When you use silver halides for photography, for example, you induce halide segregation in these materials, which are driven by the halide vacancies in the material. but I have not seen a reversible process up to now.
Yeah, very interesting data. Also relates to Bruce's question. So light comes in, and then this halide start to move around and segregate. So do they come out of crystals and then go into the environment? Would that be a degradation mechanism? So iodide certainly is well known. Light comes in and then split it, and then
Yes.
iodide goes away. You know.
Yes, we have fooled around with a few of those experiments. So for example, if you take this material and disperse it in hexanes, and over time, if you irradiate this material and you do a starch test in the hexane solution, you see iodine. So the halide will eventually leave as X dot, and two X dots will get together and form the halogen. Those are extreme cases where we basically try to decompose the material. In these materials, because we see such beautiful reversibility, I don't think the halide will leave the material.
The stability issue under moisture, have you checked that out to see how, is it worse when there's light present or not? I think all of your stuff was done in the dark.
Yeah, actually, we haven't considered the effect of light for the stability test. We just use these controlled humidity chambers. That's an interesting point. We should do this in the dark and in the light. We haven't noticed any differences that really stand out for now.
Well, if there are no more questions, let's thank him again. As I said at the beginning, we have three very different approaches to capturing solar energy and either generating electricity or a fuel. And in this talk, you'll see the biochemical perspective. Clint Chappell from Purdue University will present his work that's funded by GCEP.
All right, well, it's a pleasure to be here, and I'm grateful for the opportunity to present our work that is funded both by GCEP and also from funding through the Department of Energy. I think I could have retitled my talk now for something completely different because it's going to be a big departure from the talks we've heard so far. And that's not working. Okay. I'm probably pushing the wrong button. Or my other right. It's okay. So I'd like to give you a brief outline of what I want to talk about today. Again, this talk and our research is focused on lignin, the hardening component of the plant cell wall. What I often boil it down to is the difference between a piece of celery and a piece of wood is the presence of lignin in that cell wall. And you know what implications that has for the durability of a piece of wood, whereas a piece of celery is entirely and rapidly compostable. However, that polymer is very important to the plant, and I'll give you a short overview of that. I want to tell you why GCEP and other funding agencies have focused funding on lignin because of its plasticity, and I'm also going to tell you a little bit about what happens when we mess around with it in ways that the plant doesn't like because we can get a yield penalty. I want to tell you some of our most recent work on understanding how the plant monitors and controls the amount of lignin it deposits, and what we've found was a very unanticipated mechanism that the plant uses to control and link both metabolism and growth with regard to this aspect of cell wall deposition. And then finally, if I have time, I'll conclude by talking a little bit about opportunities for identifying new genes that we can use for engineering lignin to improve biofuel production. So this is some sort of an imaginary, if you will, representation of what the lignin polymer looks like. It's not a repeating structure, so I can't draw you a picture and say this is really what the chemical structure is. But suffice it to say it contains many different linkages by which these building blocks are linked together in ways that make that polymer very difficult to degrade. That's good for plants because it makes it difficult for fungi to degrade their cell wall, for example, or bacteria. It makes it difficult for us because we might like to degrade it to get access to the polysaccharides in that plant cell wall in order to produce cellulosic biofuels. With regard to plants, it's a very large commitment of fixed carbon, and so it's probably not a big surprise that there are extensive regulatory mechanisms in place that make sure that the plant makes enough and not too much lignin. Perhaps something in the order of 20 to 25% of photosynthate goes into this polymer in plants. As I've mentioned already, it has an important impact on bioenergy and bioprocessing because it is intimately interwoven in the plant cell wall with the cellulose and other polysaccharides that we would like to get access to for biofuel production. And then on the flip side, and another reason perhaps for it being important to understand how the plant regulates lignin biosynthesis, is that it has a very high energy density. So another approach that is being considered is trying to get more carbon into this pathway because of this high energy density of lignin as opposed to the polysaccharides. So why is this polymer important to plants? Well, it's important, the way I tend to describe it is it's important both at the macroscopic level and the microscopic level. So at the macroscopic level, the reason that these trees are the ones out in the garden here can stand upright is that they have this polymer integrated into their cell walls. At the microscopic level, though, lignin is important for rigidifying individual cells. So if I were to give you each a chocolate milkshake and a very thin-walled paper straw, it would come as no surprise to you that that straw would collapse when you tried to drink that milkshake. Well, in plants, including this plant here, oh no, that's not real. It's important to realize that water is not pushed up from the roots, but it's pulled up from the ground by the leaves. So that water is under tension in these cells. Yes, these big open cells here are the ones through which water is transported. And in a plant, this is a cross-section excuse me, of an Arabidopsis mutant that we work with. In this plant, where these cells have less lignin in them because of a block in the lignin biosynthetic pathway, these cells have collapsed because of that tension, just like that paper straw would. Important at the microscopic level and at the macroscopic level. So why are we interested? Why is there so much interest in modifying lignin? Well, an important, financially significant portion of the effort or the cost that goes into producing cellulosic biofuels is associated with processes like pretreatment. And the idea of pretreatment is to open up, expand the cell wall, disaggregate lignin from the polysaccharide components in the cell wall so that the hydrolytic enzymes that are used to release fermentable sugars from the wall, those enzymes can have access to those components. And so in this diagram here, the idea is that there's a certain amount of pretreatment that you can do that will give you a certain amount of sugar that you could generate a certain amount of biofuel from. If, on the other hand, you could, for example, decrease the amount of lignin in that cell wall, so the purple bars here are thinner, standing for less lignin, you might be able to use less pretreatment and save money in that processing to get the same amount of sugars out and the same amount of fuel. Or if you found a process of pretreatment that was sufficiently inexpensive, perhaps you could have a more thorough pretreatment, blow that cell wall apart, and get even higher yields of both fermentable sugars and fuels. So the problem with that is that lignin is important to plants for the reasons I've already mentioned to you. So here's the few images of our experimental system, Arabidopsis. We use Arabidopsis because it is a plant we can make very rapid experimental progress with, and the lessons that we learn with that plant can readily be transferred to actual crop plants. Our work would be much slower if we were working with something like switchgrass. At any rate, this is what's called an allelic series of mutants, and these plants have less and less and less lignin in them, in their cell walls, and what you can see is there is a definite impact on the yield of these plants. And that's perhaps not too surprising. I've already told you that water transport is very important, that lignin is very important to water transport, and so if you're interfering with that important process in plants, perhaps it shouldn't be surprising that the plants don't grow as well. And so this, excuse me, let me just go back and say this is where the focus of our work is, this idea of lignin modification induced dwarfing. So we see this, if we, in general, we see this phenomenon if we reduce the amount of lignin in plants. There are other examples that I'll show you today where we can change the quality of the lignin without having these severe effects. But this is really the topic that we're interested in investigating, and in fact, Chris McClellan from our GCEP collaborator, Claire Halpin's lab, will be speaking later today about this whole topic again, and I think perhaps might even be mentioning his research with this particular mutant of Arabidopsis. So, I've taught undergraduates biochemistry not long enough to know that few people are interested in actually looking at chemical structure, so I have reduced over the years my biochemical pathway to this sort of schematic. And suffice it to say that this lignin biosynthetic pathway starts with phenylalanine in the top left and generates the precursors of two types of lignin that we call G and S lignin in the bottom right. And the transformations then are shown up here, that where the amino acid is hydroxylated and methylated on the ring, and the side chain is reduced to this alcohol, so that we end up with two flavors of monomers that comprise the major components in most flowering plant lignin. And so we have, in general, these are copolymers of these of coniferal alcohol and synapyl alcohol, so-called G and S lignins, respectively. So that's the biochemical pathway, but we need to consider this in the context of, in a cellular context. And so all of those biochemical processes go on within the cell at the top left here. These monomers are then excreted to the cell wall, where they're activated by peroxidases and lactases to form their free radicals, which then will spontaneously couple to generate this polymer in the wall. Now, the reason that lignin manipulation is such an opportunity is that it's a very unusual biochemical polymer. For those of you who want to think back to your biology classes, you may remember that nucleic acids like DNA and RNA, those are synthesized. So DNA is synthesized on a template of DNA. RNA is synthesized on a template of DNA. Protein is synthesized on a template of RNA. We're using that information. Polysaccharides are a bit different. Their structure is very carefully dictated by the enzymes that assemble them. But lignin is entirely different. Lignin is a random radical coupling process where what the lignin polymer that you get out is dependent solely on the various monomers that go in, that the plant produces. So if we go back to this slide, each of these three, this paracumal alcohol is a very minor component of most plant lignin. These are the two major ones, as I introduced before. So the ratio of these monomers synthesized determines the nature of the polymer produced. So we have a few pieces of experimental evidence that backs that up. So for example, one of the things that's really fun that we can do in Arabidopsis is that we work with mutants that are blocked in these biochemical pathways. I showed you one before, those various dwarfed mutants. But we identified a mutant that was blocked at this one step called F5H, which is required for the synthesis of syringil lignin. And if you knock that gene out, what you get is a lignin that's produced only from these G subunits. These plants, as I'll show you in a minute, grow perfectly fine. Perhaps not surprising because that pine tree out there also makes lignin that's only derived from G subunits. So we know that's a functional polymer. If we instead overexpress this particular gene, what we find is that we can reroute carbon just to these S subunits and make a polymer derived only from S subunits. And as I said, these plants, this is just a photo of normal plants and the plants that make only the G lignin. The S lignin synthesizing plants look just the same. These plants tolerate this change in lignin very well. And in fact, we've taken that technology and transferred it to poplar, which is a bona fide bioenergy crop. And the easiest way for me to show you what the impact of that biochemical change in lignin is to show you these samples of paper made from these modified lignin poplars. The wild type plants here with normal types of lignin, you can see this brown coloration is because of the residual lignin left in this paper. That's why paper towels are brown in color. But under the exact same conditions, the high S lignin poplar wood is white because all of the lignin can be removed. So there's a very distinct impact of this change in lignin chemistry on our ability to remove it. And that's where, although this example comes from pulp and paper, we can expect similar impacts with regard to biofuel production. Okay, so those were the good stories. The interesting thing, or an interesting thing, came when we looked at mutants that were blocked earlier in this pathway. If you block C3'H, again, we identified a mutant that was blocked here. What we found was that these plants started making lignin from this subunit that I told you was a very, very small component of wild-type lignin, less than 1%. But the narrow line I've shown here is meant to represent that the flux to lignin, the total amount of lignin synthesized, was dramatically reduced. And the impact on growth was apparent. Okay, so I don't even know if you can see this little thing here, but that's the mutant that is blocked at C3'H. So there's a very significant impact on yield. And if you talk to a plant breeder, they will tell you there are 3 things that are important in breeding crops: yield, yield, and yield. So this is a very important thing for us to get a handle on and to understand why this particular change would lead to such a dramatic phenotype. I would say, though, also that, I won't show you the data, but these plants also, as I said, have lower levels of lignin. They have collapsed xylem, the paper straw issue again. And so perhaps, again, it's not a big surprise that these plants don't grow well. They can't transport water properly. So this is where this particular story, if you will, collided with another piece of research going on in my lab. One of the interesting things about taking a genetic approach to understanding plant biology is that instead of being theory-driven, as many of the talks that we've heard over the last 2 days are, when you use genetics, you let the organism tell you what's important. So we identified another mutant that had lower levels of lignin, like some of the ones I've already told you about today, and that also showed this phenotype where this low level of lignin in the water-conducting cells led to a collapsed vasculature. We didn't know what this particular mutant was, of course, when we first identified it, but we have technologies for going from a mutant phenotype to a gene, and we succeeded in doing so, and we found that because the Arabidopsis genome has been fully sequenced, we can move this sort of science along quite quickly. We found that this gene that we called REF4 had a paralog, another gene quite like it, that we called REF4-related 1, or RFR1. And what we found was that when we knocked those genes out, so this is a REF4 knockout, this is an RFR1 knockout, this is a plant in which we've combined both of these knockouts into the same plant. Those plants didn't look the same as this initial mutant that we identified. This is this mutant with low lignin, collapsed xylem, and again, it's dwarf. These ones are not. But when we did some biochemical analyses of these plants, and this is using, oh boy, did that axis ever get messed up. Never mind. This is looking at a soluble metabolite that's derived from the same pathway as lignin. We found that our original mutant had lower levels compared to a wild-type plant, but when we knocked out those genes, the accumulation of this compound went very much higher. So, if you will, what we have, if I try and make a traffic light analogy, is that in these plants, this metabolic pathway leading to that soluble metabolite I told you is being properly regulated. Not too much, not too little, but it's under active regulation. When we knock these genes out, then the pathway is elevated in expression and activity, and we get higher levels. The plant is moving forward with that biochemistry to a greater extent. And when we have this particular mutant, the mutation in this particular gene has has put a constitutive brake on the pathway. And so there's clearly something that's very important about this protein that acts in a regulatory role in this biochemical pathway. So what does this gene encode? It turned out that this gene encodes a component of what's called the mediator complex. The mediator complex is one that binds upstream of genes. So in this particular diagram, we have a gene illustrated down here. This is the mediator complex. It's about 30 proteins that get together to interact with proteins that called transcription factors that regulate the expression of genes. So you can imagine, and it's the case, that there are proteins that bind upstream of genes that tell the cellular apparatus how much of a particular gene to make, under what stimuli, abiotic stress or biotic stress, and in what cell types. And what this mediator complex does is that it integrates all of that information to come up with some sort of a concerted output of gene expression. And apparently this particular mediator component, which is this one called MED5, is important in regulating this lignin biosynthetic pathway. So, as I said, some of our work sort of collided in this project. And so one of my postdocs asked the question, well, if this mutant that is blocked early in the pathway that is so dwarf is somehow perturbed in the regulation of lignin synthesis, and this protein called Ref4, or we now call it MED5 now that we know what it does, is an important regulator of the pathway. Is there any interaction between these? Can we test that in vivo? And so what he did was generated a mutant where both of these mediator components were knocked out and the biochemical pathway was also blocked. And so instead of being this very sad little dwarf plant, this plant can now grow. This plant is still blocked in the biochemical pathway leading to lignin synthesis, but it is no longer dwarfed in this way. And that was a totally unexpected finding. What he found was that in these plants, lignin biosynthesis was restored. So here's the low levels of lignin in the lignin biosynthetic mutant, but if you eliminate these mediator components, the lignin goes up again. The cell wall defects that we saw that associated with the collapsed xylem, so here are some TEM images of, here's the plant that has low levels of lignin and the wall is very distorted. It's restored basically to normal when you knock out these mediator components. And in work done with our GCEP collaborator, John Ralph's lab, they took a look at the lignin and found that it has an entirely different structure. It has a structure that reflects the sole contribution of these para-hydroxyphenyl units, the units that I said this plant would now make as a result of the metabolic block. What's fascinating about that is that nobody thought that this type of lignin could even be made by plants and that it would be functional. But now we have plants that make it just fine. So this is a a 2D NMR basically looking at the contribution of S, G, and H units to the lignins of wild-type plants, MED5 mutants, and this very unusual triple mutant. So in the last couple of minutes, I'll finish up just by telling you some insights that we got from doing experiments that are called RNA-seq experiments. So I'm sure you all know that there have been tremendous advances in DNA sequencing technologies in the last decade or so. Not only can we sequence DNA and get the sequence of the human genome, we can sequence the RNA made by any individual organism. So instead of telling us all of the genes in an organism, this type of experiment tells us what genes are being expressed at any particular time. So we could ask, what genes are expressed as a result of UV or insect attack or mineral deficits? Here we ask the question, what's the difference in gene expression between these mutants that we have that are either blocked in mediator, blocked in lignin synthesis, or both? And so the image on the left is the genes Venn diagram for genes that are upregulated. On the right, those that are downregulated. And what you see is that there's a huge number of genes that are upregulated and a huge number of genes that are downregulated because of this metabolic block in these original mutants. And perhaps probably the most important set of data is when we combine this mediator knockout in the same genetic background, this number 4,400 goes down to a few hundred, 3,300 goes down to 200. So whatever the responses are that lead to these changes in gene expression in this lignin mutant, they are mitigated if you knock out mediator. So our model is that, again, a model of a process that we didn't even understand existed in plants, is that when we block this biochemical pathway of lignin synthesis in the cytoplasm, changes either in cell wall chemistry or structure or soluble metabolites, and that's actually the model I prefer, are somehow detected by a sensor. This signal is transduced to the nucleus where mediator is required for changes in gene expression, and this set of changes in gene expression then have a trickle-down effect. They cause a cascade of other changes in gene expression that result in the developmental defects we see in the plant. I think the best way to think about this is to think about anaphylaxis. We know that our immune system is here to keep us healthy, but in certain individuals, when they, for example, if they have a peanut allergy, their immune system can go haywire and make them very, very ill. Here, this system is involved in keeping that phenylpropanoid gene expression at the right level, but if we have a block, we can have very severe changes in gene expression that actually end up making the plant sick. So I'm running out of time, so I'll just say that another one of our GCEP collaborators is studying what other genes may be required in this sensing pathway and has identified other mutants in which this dwarf phenotype is suppressed. These plants can now grow quite healthy, and he's in the midst of cloning these genes. And I think I better just go ahead and skip some of these data and just finish up. Some of that was on Whitney's poster yesterday, and just say that what we found is that a previously unknown regulatory circuit for that keeps lignin biosynthesis at an appropriate level, and that this involves this mediator complex. We found that we can reverse this dwarfing that we see in low lignin plants, and it's actually not simply an architectural problem, not simply caused by defects in water transport, xylem collapse. It's an active protein-mediated process. We found that we can make a whole new type of lignin that could be used in a biorefinery, and that we have an active set of feedback mechanisms and that are detecting phenylpropanoid metabolism and cell wall changes, and that's really the focus of our current GCEP work. And with that, I'll just say thank you to those people who are involved, both in at Purdue and our DOE-funded EFRC called C3 Bio, as well as my GCEP collaborators, and I'd be happy to take any questions.
Okay, do we have any questions for the speaker? Sally.
I'm not a biologist, so this is a non-biologist question. So this is really fascinating, and it seems like you've made such incredible progress. When and how would this knowledge be, moved to the next level where you could start incorporating it in, actually biofuel crops? And what's involved? Is that 50 years from now? Is that 5 years from now?
Oh, okay.
Yeah.
Yeah, it's a great question. I mean, I have one supplementary slide that, because I really wanted to keep the focus of this talk on the fact that that we've discovered a novel regulatory mechanism. It's too blunt an instrument to deploy in the field because this mediator complex is involved in regulation of many, many biochemical processes within the cell. And so, for example, we already know that these plants are more sensitive to pathogens. But what we have done is a simple experiment to ask, does this change in lignin? Now we have plants that make pure H lignin. Is there any direct application for that? And what we found is that even if you don't do pretreatment, the dotted line on the left shows that we can release more sugars from the cell wall with this novel lignin than if we have the typical GS lignin of wild type plants. So that says, we're making a step in the right direction. And so what becomes really important is that we study this system, identify some of the other players, and identify those tools that will allow us to get a better handle on controlling lignin synthesis and this dwarfing without leading to these pleiotropic phenotypes like pathogen susceptibility. So, it used to be that not so long ago, cloning one of those genes was the work of, that was a PhD in biology. Whitney cloned 15 of them in a month, not too long ago, and I had to skip over some of that data for the sake of time. So the rate at which we can bring these genes, this knowledge to bear is very much reduced, and so that's where the exciting things come in, is how can we take this information, integrate it into things like breeding schemes to really improve biofuel crops.
I have kind of an off-the-wall question.
Well, it was an off-the-wall presentation, so.
It was really interesting. So if you drop an atmosphere, you get about 10 meters of height with water. And so you say that the height of plants is limited by their ability to withstand the strength of being able to pull the water up. But yet trees go to 10 times that height, roughly, with some other mechanism. Have you thought about trying to incorporate those other mechanisms to combat the dwarfism associated with weak cell walls?
Okay. So those weak cell walls are collapsing under water potentials that are very, very low. I mean, a Arabidopsis only gets this big. So that issue of how far can water move up a capillary in this country, it doesn't come into play. Lignin is important for not just that structural support, but the making the vasculature more hydrophobic so that you don't get adhesion of water to the very hydrophilic polysaccharides in the cell wall. I don't know that, we don't know to what extent that is tied into limitations on how tall plants can grow.
Hi, Clint. Hi, this is kind of a random question as well. There's quite a few examples of knockouts in genes that give different types of lignin, less lignin, H lignin, and examples where sugar is released more easily. So do you have a feel for, at this stage, what you would like to see in a crop? Like what modifications you think would work in terms of a biofuel crop? What would be optimal? Do you think it would be one modification or there'd be several? And this would be something you might learn over the next few years?
Yes. So we know, for example, that if you block the lignin biosynthetic pathway very early, such that the plant simply cannot make it no matter what you do. These mediator knockouts do not rescue that phenotype. So at some level, lignin is required. I think what's exciting about this is that this research gives us the opportunity to revisit technologies that had been discovered and abandoned because of the deleterious phenotypes that were associated with them. We're now going back in the lab and revisiting those and asking how many of those dwarf low lignin plants or altered lignin plants, how many of them can be rescued with this type of an approach so that we can think about taking those abandoned technologies off the shelf and incorporating them into breeding programs.
Question about the, actually you've displayed a very interesting thing about evolution, perhaps, exposed why there are all these different pathways and what has actually been selected over the millennia to be the one that's preferred by the particular plant, right? So, but my fundamental question is, we learned from the corn ethanol problem that caused a lot of malnutrition around the world, that getting 7% of sunlight to produce sugars and then spending energy to extract and then ferment and then mix with a little gasoline to denature it and burn it at less than 1% net efficiency is really not the way to go. So what do you think overall this says about biofuel idea, which I don't feel makes a heck of a lot of sense, but.
Yeah, so I think there's certainly many varying opinions on that issue. I guess I would argue that it's too early to abandon any type of technology. We have been, if you think about corn, we have been breeding corn for 5,000 years for grain characteristics. And still, over the last 80, 90 years, the theoretical grain yield has been increasing steadily. So there's a huge opportunity there. We have been breeding plants for their cell wall characteristics for essentially 0 time. And so, at the end of the day, it may be the case that what we really need to do is improve the caloric value of the plant cell wall by increasing lignin synthesis. Important to understand how it's regulated. Combust it, do something with it, sequester that carbon. The fact is that as I understand it, there is no technology that competes for recapturing CO2 from the air, which is a problem that we're going to have to tackle, that competes with photosynthesis. So at least for the time being, that's a way to think about it. But whether biological conversion like fermentation or catalytic conversion is another thing that we're exploring. How those will turn out, it remains to be seen. But I think it's still an area worth investing in.
Okay, our time is up for now, but I'm sure the speaker will stay around to answer questions during the break. Let's thank him one more time.